Here's an update of ADS version 1.2.89. This release includes a few updates. One of them is the cube, sphere, and cylinder support mirror meshing. So I can move the mirror mesh and it will replicate the geometry. Another feature is updated support for a step file, import and exports. So many more object types in step file format are supported. And the other feature that is in beta is a 5-axis router. So currently we have 3-axis support, and the new 5-axis router has global settings that let you configure the particular machine. So the bed dimensions will limit the size of the model. Once you generate the G code, it's important that the toolpath doesn't go outside of the bounds or it will crash the machine. So the bed dimensions you can enter are width, depth, and height. The coordinate system isn't implemented yet, but it will be a way to configure your particular machine. So if the B or C axis, the direction for the origin, or you can also invert the rotation directions so that the G code that you generate from ADS will map to your configuration on your hardware so that you don't have to change the controller on your hardware. This isn't implemented today, but it will be at some point. Rotor dimensions lets you configure the size of the physical rotor so that it can do its collision detection and generate the toolpath without collisions. Bits allows you to define each of the tool bits for the passes. Right now there's 6 supported. We have ball nose and flat end, and you enter the dimensions and then you can generate the toolpath. So right now there are 2 toolpath options. Firstly, you'll want to run a roughing pass to remove the material. It's going to construct a rectangle the size of the contents of the scene. C is the rotation on the vertical axis. B is rotation on the Z or depth. T, the tool, is one from your configuration. The accuracy is the units spacing between each pass. The speed is in the units of the machine. The RPM is the spindle RPM. The depth is the amount of material to be cut for each pass. And it's important that the depth is not longer than the cutting length of the drill bit. So based on the angle of B and C, it'll give you a hint as to what the highest depth that you can cut. The markup will just show an illustration or a simulation of the cutting path. So I will click OK. And you can see the angle from the top. This is the 15 degrees. And you can see the tool is pointing in at 45 degrees. So normally the roughing passes, we would usually have the tool bit pointing down, but it all depends on the geometry or the part that you're cutting. So right now it's modifying the toolpath to remove collisions. Most of the geometry of the rotor is far away from the drill bit. You can see that the cutting area is in red. And it's modifying the toolpath that you can see as this line so that there aren't any collisions. Normally we wouldn't run the C at 15 degrees. This is just for illustration so that you can see. It probably makes more sense to run it at 0 degrees or 90 degrees. So in this case we've got two layers. It does take a long time. I'll just let it finish. Right now it spits out debug information for how it calculates the toolpath, and then this is the geometry of the router that it will use for the collision detection. So we want to cut the surface of the model We don't want the drill bit to protrude through the part. So the final pass is running through the generated code, and it's just going to do a final check to make sure that there aren't any collisions. And when it's done, it's going to spit out the G-code. So you can see the G-code here. So now that we have the roughing pass, it will cut the material away, but it will leave a small gap between the surface of the part and the drill bit. So this gap right here is purposefully left a small amount of material. The idea being that when running a roughing pass, we're going to run it as fast as we can, and the gantry and the drill bit can wobble slightly at high speeds, so we want to leave a little bit of padding. And then when we run a finishing pass, we're going to use the same orientation, the same tool, the same accuracy, and we will run that. So it starts in the X0 and Z0 coordinate so that you can align the block. And it's done. So the final pass is just another check. There we go. And then the finishing pass. So it will tell us that it estimates 9 minutes to cut this part, and we wouldn't actually use this B and C direction to cut this part. It would probably be straight up and down. But other parts we will run multiple finishing passes with different B and C angles so that we can get in at different areas that normally a 3-axis router can't access. So this is the first version. It will be used for our shop. We have a 5-axis router. We're going to be making parts with this, and we will be improving the product based on the lessons that we're learning. We're also using the Fusion 360 manufacturing plugin for the G-code generation. One of the things that we'll be using this in some cases to make the parts, but we also have a tool in the CAM for the G-code post-processor to do conversions from the G-code that Fusion 360, the manufacturing plugin, generates, but it generates the G-code in the TCP format. So our machine has a controller using Mach 4, and we can't run TCP code. So we load it in this program here, and we can enter the information about the geometry, the length between the fulcrum, the BC length, and the tool tip, and we can do some orientation, modify the coordinate points, and then save it, and then we can load it in our controller. So you can use our 5-axis or 3-axis G-code milling features, or you can also use our post-processor to run Fusion-based 5-axis G-code on a commercially or your custom 5-axis router using Mach 4. And that's it for this release.